So in this chapter, we talk a little bit about how we study economics. And really, it's not much different from how scientists study the things they study, how a physicist studies physics or a chemist studies chemistry. So we follow very closely with the scientific method that you've probably been exposed to in other classes. So the first step of that is to observe a phenomenon. So for example, you observe that people are buying more hybrid cars, or hybrid automobiles in general, cars and trucks. So then you develop a hypothesis, a guess about why this might be. So maybe your hypothesis is people are buying more hybrid automobiles because the price of hybrids has fallen, or maybe people are buying more hybrid automobiles because the price of gasoline is higher, or maybe a combination of both. So you develop a hypothesis, a guess that's somewhat educated, a guess based on the information that's available to you. Next, you construct some model to test this hypothesis. So you think about maybe the supply and demand model from economics, which we'll study in the next chapter, and you think about how when the price of a hybrid falls, how that might change the quantity that people want to buy. And so you have some theoretical model that says, in theory, this is how these relationships should work. So if you think about the way a chemist does this, they notice that when you add the red solution to the blue solution, you have an explosion, right? So their model may be something at the molecular level that shows how different atoms or molecules interact with each other theoretically. When the molecules from the red solution encounter the molecules from the blue solution, what can we expect to happen based on what we know about the properties of those molecules? So you have some theoretically, this is what we would expect to happen. And then the next step is you look for some opportunity to test how well that model works, or you devise an experiment, in other words. So in chemistry, you would go back to the lab and you would try over and over mixing the red and the blue to see if every single time you get the same result. Maybe you mix a little bit of red with a lot of blue, or a little bit of blue with a lot of red, or you do different versions of your mixing. You devise an experiment, though, to try to gather some data to see, does this happen every time, and does the real world match my model? So in the case of our economics experiment with the hybrid vehicles, we can gather data on car prices, and gather data on gasoline prices, and gather data on the hybrid sales, and any other variables that might be interesting to us. And we can use statistics to look and see, is it true? Is our hypothesis correct that when car prices, when hybrid car prices go down, hybrid car sales go up? When gasoline prices go up, hybrid sales go up, right? So we can compare the real world data and use some statistics and try to draw some conclusions about whether the real world works like our theoretical model did. And is our hypothesis then something that we can validate using data? So the last step there then is that we revise or refute our theory based on the evidence. If we were to go to the lab and dump red and blue together again and now they don't explode, we'd have to go back and rethink our theory, right? So maybe our hypothesis was wrong. Maybe it had something to do with the temperature in the room and not just the red and the blue, things like that. So that's really a cyclical method, that you're always going back and you're thinking again about those things. So in the beginning, when we're devising our hypotheses, they could be one of two types of statements. It could be a positive statement or a normative statement. And this is not positive versus negative, it's positive versus normative, right? So a positive statement is a statement that can be tested, a statement that can be validated, describes what is true. So for example, income in the United States has been increasing. It may be true or it may be false, but at least it's something we can test. So it's a positive statement, as opposed to a normative statement, which is more like an opinion. It can't be tested or validated. It describes maybe what you think ought to be. So for example, the United States should send foreign aid to other countries. It's a should statement. It's not something we can prove to be true or false. It's not something we can even test to see if it might be true or false. It's a should statement. It's an opinion or a normative statement. So take a minute, pause this video, and look through these examples of statements. Decide whether each one is positive or normative. Okay? Did your answers match these? So rich people should be taxed more. It's a normative statement. It's an opinion. It's a should statement. We can't test it. We could test something like the next one, which says more taxes on the rich will increase tax revenues, right? We can actually look at data and see what happens to tax revenues when we increase taxes on the rich. But then the question of whether or not we should do that is up to someone else, right? That's a question. Is increasing tax revenues a good thing or a bad thing? Is increasing tax revenues worth it for what damage we might do by raising taxes or whatever, right? So the should statement is much more involved than the positive statement there, that more taxes on the rich will increase tax revenues. And the next one, everyone should donate to charity. That's a normative statement, another should, ought to be type question. Government intervention in markets is bad. This one's a little tougher, but it's normative because the definition of the word bad depends, right? What does it mean for something to be bad or good? It's a normative word, the word bad. And lastly, economics majors earn more on average than sociology majors do. I don't know if that's true or false, but it's certainly something that we could test. We could look at the data and find out if that's true or false. And so it's a positive statement. Now, economic models are simplified versions of the real world. We use simplified versions of the real world in order to help us understand things that are too complex in the real world for us really to study by just looking at them. So models then make a lot of assumptions in order to simplify reality. Good models, though, are simple. They're flexible. We can add some things to them and see how they react, or take some things out of them and see how they react. And they're accurate in making predictions. When we have a model, it's only useful to us if it's accurate in making predictions. So an example of a model that you encounter every day will be a map, right? If you were trying to plan a spring break trip from Georgia to Oklahoma, and you just went and looked out your front door and looked toward the west, toward Oklahoma, it'd be really difficult for you to plan your trip just looking at the real world. And so we take a model of the real world, a map, which is a smaller version, and it's a version that leaves a lot of things out, right? So we'd leave out the hills and the valleys and the atmosphere and the trees and the things that are between your front door and your destination that keep you from being able to plan your trip by just walking out and looking to the west. We'd simplify the real world into a small version of reality that then, if you were, say, taking a bike, you might want to know where those hills and valleys are. And so you could add contour lines that would show the altitude of different areas of the country. And so it's a flexible model. You can add or take out things from a map depending on what you need. But ultimately, a map is only good if you can use that map to get from your front door to Oklahoma. It's only useful to you if it's actually accurate in getting you where you're trying to go. So in order to make a model, to make a simplified version of the world, we have to be able to make certain assumptions, simplifying assumptions. One of those that's particularly important that we return to over and over is the assumption of ceteris paribus, which is Latin and just means other things being equal. It's a central assumption in model building, and it allows us to study the effect of just one variable by holding everything else constant. So if we go back to our model about hybrid vehicles, and you want to know if it's true that when gas prices go up, people buy more hybrid vehicles, right? In order to study that relationship, you need to be able to assume that other things stay constant. Because what if gas prices go up, but also there's a hurricane? Or gas prices go up, but also there's a huge recession and people's incomes go way down, right? There are other things that may be happening that could affect people's ability or desire to buy hybrid vehicles. And you want to be able to hold those things constant to really study the relationship between gas prices and sales of hybrid vehicles. And so you can do that in your model with the ceteris paribus assumption. It's some fancy statistics that we won't get into that you can talk about in your stats class. But if you design your model correctly, you can use statistical tools to then hold everything else constant and only look at that relationship between the price of gas and the sales of hybrid vehicles. So how do you do that? How do you get the statistics to do that? You have to be careful about what factors you do and don't include in your model. So if you're building a map, you got to be careful about what things you decide to include on your map and what things you decide to exclude on your map. You're probably going to include a scale of some sort that makes your map smaller than the real world. You probably won't include all the trees that complicate the real world, right? Unless you're building a model for a very specific reason that needs the trees, right? So you've got two types of factors in the world. You've got the endogenous factors, the variables that you can control for inside your model. And you've got exogenous factors, variables that you can't account for or that you're choosing not to account for in your model. So in our model for studying the relationship between gas prices and sales of hybrid automobiles, you would definitely want to include gas prices as an endogenous factor, a variable that you are controlling for using statistics because you want to see that relationship. You probably also want to include some measure of overall economic situation. So are we in a recession or not, sort of variable that you would want to include. You may also want to include the price of cars or the price of hybrid cars as another thing that you can control for in your model that might affect your sales of cars, of hybrid cars. So you want to be sure that you include all the endogenous factors that are important, but you want to leave out exogenous factors, variables that can't be accounted for or that you just don't want to account for because they're so small in their ability to affect your outcome variable. The more exogenous variables you have in your model, the more realistic the model becomes, which is a trade-off, because the more realistic your model is, the harder it is to use, right? Remember, one of the important things about models is that we keep them simple. So you want to include the very important things while excluding the things that aren't important, which is a hard call sometimes. This is one of those times when this class can help you be a better consumer of information. When you're watching the news or reading a newspaper and you read about a study that that had some conclusion about why people are buying more or fewer hybrid vehicles, you want to be able to ask the question, well, what variables did you include in your model? Did you think about whether there was a hurricane or not? Did you think about whether we were in a recession or not? Did you think about the price of non-hybrid cars? And if the answer is no, you want that researcher to be able to tell you why they left those variables outside their model. Because only the variables they included in their model are things that they're able to hold constant with ceteris paribus. The exogenous factors, the ones that aren't included, are things that they're not being able to control for using those statistical tools. But at the same time, you don't want them to throw in every variable possible, because that makes their model much more complicated and tough to use. You don't want a map that is exact mirror of the real world, because then it's not helpful anymore, because you can't just walk out at your front door and look at Oklahoma. So it's very important when you're building a model to decide what variables you include and what variables you exclude. You do not want to leave out any important variables. You also don't want to include any unimportant variables. But it's a judgment call for you, the researcher. Oftentimes it takes a lot of playing with data. Put in the variable and see if it seems important or not, and then maybe take it back out if it's not important. But these are questions you should know to ask anytime you see a model, anytime you see a study that uses statistics to study a particular thing. So here's an example. Question that economists have asked over and over: who gets paid more? An educated or an uneducated individual? A skilled or an unskilled individual? A worker right out of college or an older worker? A new employee or a veteran employee? Someone in a safe job or a dangerous job? Who gets paid more? And the truth is, each of these lines is very important in determining someone's wage. And so if you were to build a model of how wage is determined, you want to be sure you take all of these things into account. You want to include education, age, experience, skills, working conditions, and gender all as endogenous in your model. But you're leaving some things out at the same time, right? So you can probably think of other things that determine whether someone gets paid a lot or not. Are you the boss's son, right? Do you live in Georgia or do you live in New York? Location, right? And so there are certainly other factors that affect someone's wage, but we have to make the call of whether those factors are important enough to include in our model, because we know that the more things we include in our model, the more complicated our model gets. But we do want to be sure that we're including the important things, right? And so in this model, for example, if I want to know the effect of age on someone's wage, I want to be sure that I include as endogenous variables these other things: education, experience, skills, working conditions, and gender, so that I can use statistical tools to hold those other things constant, so that I can determine the effect of age on wage ceteris paribus, holding everything else constant. Because it doesn't make sense to think about the wage of a 30-year-old with a master's degree versus a 25-year-old with just a high school diploma, right? Because then you're confounding the effects of both age and education It's hard to tell what really is the effect of age when they have different levels of education. So that's why it's important that my model is able to hold education constant. And so using statistical tools, as long as I've got education included in my model as an endogenous variable, statistics lets me then compare a 25-year-old with a high school diploma to a 30-year-old with a high school diploma. So I'll be comparing two people who are identical on all my other endogenous factors and only differ on age, so that I can see really zero in on the effect of age without those other things confounding it. So this is why it's really important to include the right things in your model. You do want to include the right things. You just also want to exclude the right things. You don't want to make your model unnecessarily complex by adding in small things that don't have as big of an effect on wage or don't matter so much to how much someone is getting paid. So it's really sort of nuanced and takes a lot of practice to figure out what to include in a model, what not to include in a model. We're not going to worry too much about the specifics of how to do that and stuff, but the main takeaway I want for you from this is that you know you should be asking these questions. Anytime you see a model, anytime you hear someone's results of their study, you should always know to ask, what things did you include in your study? What did you think about? And what did you choose to leave out of your model? And why did you make those choices?